The goal of this video is to provide more details about the implementation of the quicksort algorithm, and in particular here we're going to drill down on the key partition subroutine. So let me remind you what the job of the partition subroutine is in the context of sorting an array. So recall the key idea in quicksort is to partition the input array around a pivot element. So this has two steps. First, you somehow choose a pivot element. And in this video, we're not going to worry about how you choose the pivot element. For concreteness, you might just want to think about you pick the first element of the array to serve as your pivot. So in this example array, the first element happens to be 3, so we could choose 3 as the pivot element. Now, there's a key rearrangement step. So you rearrange the array so that it has the following property. Any entries that are to the left of the pivot element should be less than the pivot element, whereas any entries which are to the right of the pivot element should be greater than the pivot element. So for example, in this version of the second version of the array, we see to the left of the 3 is the 2 and the 1. They're in reverse order, but that's okay. Both the 2 and the 1 are to the left of the 3, and they're both less than 3. And the 5 elements to the right of 3 they're jumbled up, but they're all bigger than the pivot element. So this is a legitimate rearrangement that satisfies the partitioning property. And again, recall this definitely makes partial progress toward having a sorted array. The pivot element winds up in its rightful position. It winds up where it's supposed to be in the final sorted array, to the right of everything less than it, to the left of everything bigger than it. Moreover, we've correctly bucketed the other n-1 elements to the left or to the right of the pivot according to where they should wind up in the final sorted array. So that's the job that the partitioning subroutine is responsible for. Now what's cool is we'll be able to implement this partition subroutine in linear time. Even better, we'll be able to implement it so that all it does really is swaps in the array. That is, it works in place. It needs no additional, essentially constant additional memory to rearrange the array according to those properties. And then, as we saw in the high-level description of the quicksort algorithm, what partitioning does is it enables a divide and conquer approach. It reduces the problem size. After you've partitioned an array around the pivot, all you got to do is recurse on the left side, recurse on the right side, and you're done. So what I owe you is this implementation. How do we actually satisfy the partitioning property, stuff to the left of the pivot smaller than it, stuff to the right of the pivot bigger than it, in linear time and in place? Well, first let's observe that if we didn't care about the in-place requirement, if we were happy to just allocate a second array and copy stuff over, it would actually be pretty easy to implement a partitioning subroutine in linear time. That is, using O of n extra memory, it's easy to partition around a pivot element in O of n time. And as usual, probably I should be more precise and write theta of n in these two cases. That would be the more accurate, stronger statement. But I'm going to be sloppy, and I'm just going to write the weaker but still correct statement using big O. Okay, so big O of n time using linear extra memory. So how would you do this? Well, let me just sort of illustrate by example. I think you'll get the idea. So let's go back to our running example of an input array. Well, if we're allowed to use linear extra space, we can just pre-allocate another array of length n. And then we can just do a single scan through the input array, bucketing elements according to whether they're bigger than or less than the pivot. And so, for example, we could fill in the additional array both from the left and the right using elements that are less than or bigger than the pivot, respectively. So, for example, we start with the 8. We note that the 8 is bigger than the pivot, so we put that at the end of the output array. Then we get to the 2. The 2 is less than the pivot, so that should go on the left-hand side of the output array. We get to the 5. It should go on the right-hand side, and the 1 should go on the left-hand side, and so on. When we complete our scan through the input array, there'll be one hole left, and that's exactly where the pivot belongs, to the right of everything less than it, to the left of everything bigger than it. So what's really interesting then is to have an implementation of partition which is not merely linear time, but also uses essentially no additional space, that doesn't resort to this cop-out of pre-allocating an extra array of length n. So let's turn to how that works, first starting at a high level, then filling in the details. So I'm going to describe the partitioning subroutine only for the case where the pivot is in fact the first element. But really this is without loss of generality. If instead you want to use some pivot from the middle of the array, you can just have a pre-processing step that swaps the first element of the array with the given pivot and then run the subroutine that I'm about to describe. Okay, so with constant time pre-processing, the case of a general pivot reduces to the case of where the pivot is the first element. So here's the high-level idea, and it's very cool. The idea is we're going to be able to get away with just a single linear scan of the input array. So at any given moment in this scan, which is just going to be a single for loop, we'll be keeping track of both the part of the array we've looked at so far and the part that we haven't looked at so far. So there's going to be two groups, what we've seen, what we haven't seen. Then within the group we've seen, we're going to have that be split further according to the elements that are less than the pivot and those that are bigger than the pivot. So we're going to leave the pivot element just hanging out in the first element of the array until the very end of the algorithm when we correct its position with a swap. And at any given snapshot of this algorithm, we will have some stuff that we've already looked at and some stuff that we haven't yet looked at in our linear scan. Of course, we have no idea what's up with the elements that we haven't looked at yet. Who knows what they are and whether they're bigger or less than the pivot. But we're going to implement the algorithm, so among the stuff that we've already seen, it will be partitioned in the sense that all elements less than the pivot come first, all elements bigger than the pivot come last. And as usual, we don't care about the relative order amongst elements less than the pivot or amongst elements bigger than the pivot. So summarizing, we do a single scan through the input array. And the trick will be to maintain the following invariant throughout the linear scan. That basically everything we've looked at in the input array is partitioned. Everything less than the pivot comes before everything bigger than the pivot. And we want to maintain that invariant, doing only constant work and no additional storage with each step of our key for loop, each step of our linear scan. So here's what I'm going to do next. I'm going to go through an example and execute the partition subroutine on a concrete array, the same input array we've been using as an example thus far. Now maybe it seems weird to give an example before I've actually given you the algorithm, before I've given you the code, but doing it this way, I think you'll see the gist of what's going on in the example, and then when I present the code, it'll be very clear what's going on. Whereas if I presented the code first, it might seem a little opaque when I first show you the algorithm. So let's start with an example. Throughout the example, we want to keep in mind the high-level picture that we discussed in the previous slide. The goal is that at any time in the partition subroutine, we've got the pivot hanging out in the first entry. Then we've got stuff that we haven't looked at. So of course, who knows whether those elements are bigger than or less than the pivot. And then for the stuff we've looked at so far, everything less than the pivot comes before everything bigger than the pivot. This is the picture we want to retain as we go through the linear scan. As this high-level picture would suggest, there's two boundaries that we're going to need to keep track of throughout the algorithm. We're going to need to keep track of the boundary between what we've looked at so far and what we haven't looked at yet. So that's going to be, we're going to use the index j to keep track of that boundary. And then we also need a second boundary for amongst the stuff that we've seen, where is the split between those less than the pivot and those bigger than the pivot. So that's going to be I. So let's use our running example array. So stuff is pretty simple when we're starting out. We haven't looked at anything. So all of this stuff is unpartitioned. And I and j both point to the boundary between the pivot and all the stuff that we haven't seen yet. Now to get a running time which is linear, we want to make sure that at each step we advance j. We look at one new element. That way in a linear number of steps we'll have looked at everything and hopefully we'll be done and we'll have a partitioned array. So in the next step we're going to advance j. So the region of the array which we haven't looked at, which is unpartitioned, is one smaller than before. We've now looked at the 8, the first element, after the pivot. Now the 8 itself is indeed a partitioned array. Everything less than the pivot comes before everything after the pivot. Turns out there's nothing less than the pivot. So vacuously this is indeed partitioned. So j, recall, delineates the boundary between what we looked at and what we haven't looked at. I delineates amongst the stuff we've looked at, where is the boundary between what's bigger than and what's less than the pivot. So the 8 is bigger than the pivot, so I should be right here. Okay, because we want I to be just to the left of all the stuff bigger than the pivot. Now, what's going to happen in the next iteration? This is where things get interesting. Suppose we advance j one further. Now the part of the array that we've seen is an 8 followed by a 2. Now, an 8 and a 2 is not a partitioned subarray. Remember what it means to be a partitioned subarray. All the stuff less than the pivot, all the stuff less than 3 should come before everything bigger than 3. So A2 obviously fails that property. 2 is less than the pivot, but it comes after the 8, which is bigger than the pivot. So to correct this, we're going to need to do a swap. We're going to swap the 2 and the 8. That gives us the following version of the original array. So now the stuff that we have not yet looked at is 1 smaller than before. We've advanced j. So all this stuff is unpartitioned. Who knows what's going on with that stuff? J is 1 further entry to the right than it was before. And at least after we've done this swap, we do indeed have a partitioned array. So post-swap, the 2 and the 8 are indeed partitioned. Now remember, I delineates the boundary between amongst what we've seen so far, the stuff less than the pivot, less than 3 in this case, and that bigger than 3. So I is going to be wedged in between the 2 and the 8. In the next iteration, our life is pretty easy. So in this case, in advancing j, we uncover an element which is bigger than the pivot. So this is what happened in the first iteration when we uncovered the 8. It's different than what happened in the last iteration when we uncovered the 2. Okay, so this case, this third iteration is going to be more similar to the first iteration than the second iteration. In particular, we won't need to swap, we won't need to advance I, we just advance j and we're done. So let's see why that's true. So we've advanced j, we've done one more iteration, so now the stuff that we haven't seen yet is only the last 4 elements. So who knows what's up with the stuff we haven't seen yet. But if you look at the stuff we have seen, the 2, the 8, and the 5, this is in fact partitioned, right? All the numbers that are bigger than 3 succeed, come after all the numbers bigger than, smaller than 3. So the j, the boundary between what we've seen and what we haven't, is between the 5 and the 1. And the I, the boundary between the stuff less than the pivot and bigger than the pivot, is between the 2 and the 8, just like it was before. Adding a 5 to the end didn't change anything. So let's wrap up this example on the next slide. So first, let's just remember where we left off on the previous slide. So I'm just going to redraw that same step after 3 iterations of the algorithm. And now notice in the next iteration we're going to again have to make some modifications to the array if we want to preserve our invariant. The reason is that when we advance j, when we scan this 1, now again we're scanning in a new element which is less than the pivot. And what that means is that the partitioned region, or the region that we've looked at so far, will not be partitioned. We'll have 2, 8, 5, 1. Remember, we need everything less than 3 to precede everything bigger than 3, and this 1 at the end is not going to cut it. So we're going to have to make a swap. Now, what are we going to swap? We're going to swap the 1 and the 8. So why do we swap the 1 and the 8? Well, clearly we have to swap the 1 with something. And what makes sense? What makes sense is the leftmost array entry, which is currently bigger than the pivot, and that's exactly the 8. Okay, that's the first leftmost entry bigger than 3, so if we swap the 1 with it, then the 1 will become the rightmost entry smaller than 3. So after the swap, we're going to have the following array. The stuff we haven't seen is the 4, the 7, and the 6. So the j will be between the 8 and the 4. The stuff we have seen is the 2, 1, 5, and 8. And notice that this is indeed partitioned. All the elements which are less than 3, the 2 and the 1, precede all of the entries which are bigger than 3, the 5 and the 8. I, remember, is supposed to split, be the boundary between those less than 3 and those bigger than 3, so that's going to lie between the 1 and the 5. That is 1 further to the right than it was in the previous iteration. Okay, so because the rest of the unseen elements, the 4, the 7, and the 6, are all bigger than the pivot, the last 3 iterations are easy. No further swaps are necessary. No increments to I are necessary. J is just going to get incremented until we fall off the array, and then fast forwarding, the partition subroutine, or this main linear scan, will terminate with the following situation. So at this point, all of the elements have been seen, and all the elements are partitioned. J, in effect, has fallen off the end of the array, and I, the boundary between those less than and bigger than the pivot, still lies between the 1 and the 5. Now, we're not quite done because the pivot element 3 is not in the correct place. Remember, what we're aiming for is an array where everything less than the pivot is to the left of it, and everything bigger than the pivot is to the right, but right now the pivot still is hanging out in the first element. So we just have to swap that into the correct place. Where's the correct place? Well, it's going to be the rightmost element, which is smaller than the pivot. So in this case, the 1. So the subroutine will terminate with the following array: 1, 2, 3, 5, 8, 4, 7, 6. And indeed, as desired, everything to the left of the pivot is less than the pivot, and everything to the right of the pivot is bigger than the pivot. The 1 and 2 happen to be in sorted order, but that was just sort of an accident. And the 4, 5, 6, and 7, and 8, you'll notice, are jumbled up. They're not in sorted order. So hopefully from this example you have a gist of how the partition subroutine is going to work in general. But just to make sure the details are clear, let me now describe the pseudocode for the partition subroutine. So the way I'm going to denote it is there's going to be an input array A, but rather than being told some explicit link, what's going to be passed to the subroutine are 2 array indices. The leftmost index, which delineates this part of the subarray you're supposed to work on, and the rightmost index. The reason I'm writing it this way is because partition is going to be called recursively from within a quicksort algorithm. So at any point in quicksort, we're going to be recursing on some subset, contiguous subset of the original input array. L and R are meant to denote what the left boundary and the right boundary of that subarray are. So let's not lose sight of the high-level picture of the invariant that the algorithm is meant to maintain. So as we discussed, we're assuming the pivot element is the first element, although that's really without loss of generality. And in a given time, there's going to be stuff we haven't seen yet. Who knows what's up with that? And amongst the stuff we've seen, we're going to maintain the invariant that all the stuff less than the pivot comes before all the stuff bigger than the pivot. And J and I denote the boundaries between the seen and the unseen, and between the small elements and the large elements, respectively. So back to the pseudocode, we initialize the pivot to be the first entry in the array. And again, remember, L denotes the leftmost index that we're responsible for looking at. The initial value of I should be just to the right of the pivot, so that's going to be L plus 1. That's also the initial value of J, which we'll assign in the main for loop. So this for loop with J taking on all values from L plus 1 to the rightmost index R denotes the linear scan through the input array. And what we saw in the example is that there were 2 cases, depending on, for the newly seen element, whether it's bigger than the pivot or less than the pivot. The easy case is when it's bigger than the pivot. Then we essentially don't have to do anything. Remember, we didn't do any swaps, we didn't change I, the boundary didn't change. It was when the new element was less than the pivot that we had to do some work. So we're going to check that. Is the newly seen element, AJ, less than P? And if it's not, we actually don't have to do anything. So let me just put as a comment, if the new element is bigger than the pivot, we do nothing. Of course, at the end of the for loop, the value of J will get incremented. So that's the only thing that changes from iteration to iteration when we're sucking up new elements that happen to be bigger than P. So what did we do in the example when we suck up a new element less than P? Well, we have to do 2 things. So in the event that the newly seen element is less than P, I'll circle that here in pink, we need to do a rearrangement, so we again have a partitioned subarray amongst those elements we've seen so far. And the best way to do that is to swap this new element with the leftmost element that's bigger than the pivot. And because we have an index I, which is keeping track of the boundary between the elements less than the pivot and bigger than the pivot, we can immediately access the leftmost element bigger than the pivot. That's just the ith array index of that's just the ith entry in the array. Now I am doing something a little sneaky here, I should be honest about, which is there is the case where you haven't yet seen any elements bigger than the pivot. And then you don't actually have a leftmost element bigger than the pivot to swap with. Turns out this code still works. I'll let you verify that, but it does do some redundant swaps. Really, you don't need to do any swaps until you first see some elements bigger than the pivot and then see some elements less than the pivot. So you could imagine a different implementation of this where you actually keep track of whether or not that's happened to avoid the redundant swaps. I'm just going to give you the simple pseudocode. And again, for intuition, you want to think about the case just like in the picture here in blue, where we've already seen some elements that are bigger than the pivot and the next newly seen element is less than the pivot. That's really sort of the key case here. Now the other thing we have to do after one of these swaps is now the boundary between where the pivot elements, where the array elements less than the pivot and those bigger than the pivot has moved. It's moved one to the right, so we have to increment I. So that's the main linear scan. Once this concludes, J will have fallen off the end of the array, and everything that we've seen, the final elements except for the pivot, will be arranged so that those less than P are first, those bigger than P will be last. The final thing we have to do is just swap the pivot into its rightful position, and recall for that we just swap it with the rightmost element less than it. So that is it. That is the partition subroutine. There's a number of variants of partition. This is certainly not the unique implementation. If you look on the web or if you look in certain textbooks, you'll find some other implementations as well as discussion of the various merits. But I hope this gives you, this is a canonical implementation, and I hope it gives you a clear picture of how you rearrange the array using in-place swaps to get the desired property, that all the stuff before the pivot comes first, all the stuff after the pivot comes last. Let me just add a few details about why this pseudocode I just gave you does indeed have the properties required. The running time is O of n, really theta of n, but again I'll be sloppy and write big O of n, where n is the number of array elements that we have to look at. So n is r minus l plus 1, which is the length of the subarray that this partition subroutine is invoked upon. And why is this true? Well, if you just go inspect the pseudocode, you can just count it up naively and you'll find that this is true. We just do a linear scan through the array, and all we do is basically a comparison and possibly a swap and an increment for each array entry that we see. Also, if you inspect the code, it is evident that it works in place. We do not allocate some second copy of an array to populate like we did in the naive partitioning subroutine. All we do is repeated swaps. Correctness of the subroutine follows by induction. So in particular, the best way to argue it is via an invariant. So I'll state the invariant here, but mostly leave it for you to check that indeed every iteration of the for loop maintains this invariant. So first of all of the stuff to the right of the pivot element, to the right of the leftmost entry, and up to the index I is indeed less than the pivot element, as suggested by the picture. And also suggested by the picture, everything beginning with the ith entry leading just up before the jth entry is bigger than the pivot. And I'll leave it as a good exercise for you to check that this holds by induction. The invariant holds initially when both I and j are equal to L plus 1 because both of these sets are vacuous. Okay, so there are no such elements, so they're trivially satisfy these properties. And then every time we advance j, well, in one case it's very easy, where the new element is bigger than the pivot. It's clear that if the invariant held before, it also holds it at the next iteration. And then if you think about it carefully, this swap and this increment of I that we do in the case where the new element is less than the pivot, after the swap, once the for loop completes, again, if this invariant was true at the beginning of it, it's also true at the end. So what good is that? Well, if by this claim, at the conclusion of the linear scan, at which point j has fallen off the end of the array must look like this. At the end of the for loop, the question mark part of the array has vanished, so everything other than the pivot has been organized so that all of the stuff less than the pivot comes before everything after the pivot. And that means once you do the final swap, once you swap the pivot element from the leftmost entry with the rightmost entry less than the pivot, you're done. Okay, you've got the desired property that everything to the left of the pivot is less than it, everything to the right of the pivot is bigger than it. So now that given a pivot element, we understand how to very quickly rearrange the array so that it's partitioned around that pivot element. Let's move on to understanding how that pivot element should be chosen and how, given suitable choices of that pivot element, we can implement the quicksort algorithm to run very quickly, in particular on average in n log n time.